Hi, I'm Chaoran Li, a PhD student from Sunwon University of Technology. I'm very honored to introduce our work here, Cross-Language Android Permission Specification. Okay, let's start. First of all, Android framework consists of the Java API framework layer and the C language native library layer. Some Java API will access the C language native library layer. For example, the camera application will access Camera Manager, and the invocation will be bypassed to Camera Service, and finally go to the HAL. Secondly, the Android system manages access to the sensitive APIs by permission enforcement. When an application needs to use any of the protected features of an Android device, it must obtain the appropriate permissions. Most of the permission checks are defined in the Java API framework layer, well, there are several of them defined in the C native library layer. However, there is no official documentation providing the complete list of the permission-protected APIs and the corresponding permissions. There are several previous works that focus on the permission mapping extraction issues. Explorer leverages accurate static analysis on the SDK and the Android framework to generate permission specification. Arcade conducts a similar static analysis with additional attention paid to extract other security mechanisms, such as UID and PID checks. In order to overcome the limitation of static analysis, Dynamo uses dynamic analysis, aiming to obtain more accurate mapping. Patchin conducts an analysis permission specification for Android NDK. Our work fills the research gap by analyzing the native library and their communication with the Java framework to generate more comprehensive permission mapping. There is a real-world example to demonstrate our motivation. The code from lines 1 to 10 is derived from a popular photography app, Camera 360 on Google Play. The app initializes a camera manager instance and opens the camera instance by invoking openCamera method. The invocation chain then traverses along the call path through the Java framework and the native library, and finally triggers a permission check in the native library. We propose and implement a prototype native droid to address the problem that has been overlooked in previous works. The figure illustrates the overall design of native droid. Native droid contains three modules. The preprocessing module prepares the intermediate artifacts for analyzing the Android framework and native libraries. The entry point identification module finds out the entry points for both Java and native sites. The ICFG analyze module generates the cross-language ICFG and extracts permission mapping. Our pre-processing includes both Java and the native side. The Java side preparation collects intermediate Java files. Such files are generated during the compilation, and the files are the input of Java Analyzer. The native side preparation collects files that consist of clone compilation commands, which can be the input of the native analyzer. As for the entry point identification, there are AIDL-based and GI-based communication. AIDL is one of the IPC that Android adapted to enable communication for remote invocation. The left figure shows the workflow of AIDL-based and client-server model, where the Java framework works as a client requesting service from the native library. AIDL utilizes a pair of classes on Java side to communicate. An example of AIDL is shown in right figure, where the method getCameraInformation uses AIDL to implement the communication between Java and C++. GenAI also provides a cross-language interface between Java and the native code. The left figure shows the GenAI-based communication model. The GenAI-based communication starts from a registration process. The Java and C functions are linked through the Java method name, Java method signature, and pointer to native function. We further explain the GenAI-based communication with an example given in the right figure. The method in line 13 is called to register the GenAI method for radio, with the GenAI method information provided in line 14. Algorithm shows the detailed steps involved in generating cross-language SFGs. It first obtains the entry point pairs, then it conducts a forward analysis to generate SFG on the native side. In the third step, it discards SFGs that don't have security checkpoint. The native droid offers a backward analysis to build Java-side SFG. We further process some mechanisms during the cross-language SFG generation. For example, handling the service identifier, handling Android strong pointer, handling member variables, handling particular access control. The algorithm shows how to extract the protection mapping of Android API. After obtaining the cross-language SFG, we use a DFI strategy to check if there are copies between Android APIs in the Java API framework layer and security checks in the native library layer. For each node in the SFG, if it's a Java node, we will collect all its native children and obtain the security checks. Finally, each pair of Java API node and its corresponding security checks in the native side will be added into the protection mapping. In this paper, we have three research questions. Question 1. How effective is native droid in identifying permission enforcement in native libraries? Question 2. How many permission mappings can our tool identify that are not recognized by the state-of-the-practice approaches? Question 3. How can our tool contribute to real-world security evaluation? As for the experiment setting, we evaluate native droid on 5 AOSP versions. The experiment ran on a Linux server. In the table, we list the permissions that have permission checks in native libraries, including 2 dangerous permissions, 8 signature permissions, and 2 normal permissions. Signature permissions are only granted if the requesting app is assigned with the same certificate as the app that declared the permission. Normal permissions refer to the permissions with minimal risk to the system and the user's private data. Dangerous permissions are those higher risk permissions that would give access to private user data or control over the device that can negatively impact the user. In the first 4 versions of AOSP, our tool identified more than 440 APIs whose permission enforcement takes place in the native code, while in AOSP 10, native droid detects 282 APIs. The number of newly identified permissions that are missed in the previous works ranges from 9 to 12 in the 5 AOSP versions. According to the Android developers documentation, app developers should request a minimum set of permissions to complete the application functionality, as introducing additional permissions will increase the risk of privacy leak. However, developers usually request permissions that are not related to the application functionalities. To investigate the issue, we include 2 categories of Android apps in our experiment: the custom ROM apps that are pre-installed on the devices. We collect 1,035 custom ROM apps. There are other 10,000 third-party apps randomly downloaded from the Google Play Store. We identify more than 95% apps with permission or privilege issues using Arcades and Explorers mapping. Among their results, we identified that more than 66% contain false positive results caused by missing negative triggered permission mapping. In the discussion, we discuss why we have the file Android version mapping. How about the permission mapping extraction in custom ROMs? The limitation of the static analysis when extracting permission mapping. We propose a novel approach NativeDroid to facilitate the cross-language analysis of Android. NativeDroid builds cross-language SFG on the overall Android framework, Java, and native code. Based on the cross-language SFG, we extracted the native triggered permission specification and create the protection mapping in the native code to complement existing Java-based mapping. We further applied our new mapping to detect permission or privilege vulnerabilities in a large dataset that consists of more than 11,000 Android apps. We finally showed that using the mapping derived by NativeDroid can identify a significant number of false results existing in the state-of-the-art, such as Explorer and Arcade.